I could work on this for at least a month, but we're not going to have enough time for this. So I'm going to stick with basic examples, nothing super sophisticated, so you understand and appreciate the value of calculus. Okay, first of all, let's imagine that I have an exercise ball and it's flat and it needs pumping air. So I start pumping air into that exercise ball, right? Till it gets to a certain, what happens? Obviously the volume changes, right? From where it was to whatever volume. The surface of the ball changes. The radius of the ball changes. And they all change at the same time with respect to time, right? There are three variables that I just mentioned: volume, surface, and radius. And they all change at the same time, not at the same speed, but at the same time, and they're all functions of time because they change with respect to time. So they all have different rates, but they are related. They are related rates. I'm not saying that one is double than the other. I'm just saying they happen at the same time and they have some sort of relationship that we will be able to establish in all problems. We will establish a relationship between the variables. We will differentiate the relationship and then calculate something. Okay, so let's start with an example. On page 249, I'm going to start with a simple one, like 15. 15 on page 248. Let's read the problem. Two cars start moving from the same point. One travels south at 60 miles per hour, and the other travels west at 25 miles an hour. At what rate is the distance between the cars increasing 2 hours later? Okay, so just follow me. These are the two cars, just for 1 second. These are the two cars. One is going south and the other one is going west. And at some point I say, stop. This is the third variable. So first of all, their distance with respect to time changes, right? But also the distance between the two cars changes. And at some point in time I say, stop. And I look at see how fast is this distance changing at a particular instant. So there are three functions here. One, which is this one, right? Is the velocity function. The other one is the other velocity function. And this one is the distance that changes with another speed, the third function. And these are all related. So I take some notes. And here are my notes. First of all, one is moving west. The other one is moving south. They start at the same point. The one travels south at 60 miles per hour. The other one west at 25 miles per hour. At what rate is the distance between them? So I'm going to say they continue. Okay. So at some point in time, I want to measure or somehow determine how fast is this distance changing between the cars, increasing 2 hours later. 2 hours later.
So basically it's asking the distance they're separating at 2 hours.
Rate of change.
The rate of change. Okay.
The rate of change of this function 2 hours from the moment they started here. Yes, please, John.
It's 2 hours after they started.
Yes.
So it's not like they went 25 miles already.
No.
All right, so
Because it says, hold on one second, let's read one more time. 2 cars start moving from the same point. One travels south at 60 miles per hour and the other travels west at 25 miles an hour. At what rate is the distance between the cars increasing exactly 2 hours later? Please.
So if we're asking
Ready?
for the distance 2 hours later between.
How fast is the distance changing?
Yeah.
So this is a function. 1 minute after they start has a value. 2 minutes after they start has a different value. 3 minutes after they start, a different value. 4 minutes, a different value. So this is a function. So I want to determine the rate of change of this function with respect to time 2 hours later. Is that better?
your way is better.
So what can you repeat your question then?
I don't know how to ask it that would make your answer make sense. So
Okay.
I just, if you continue, maybe I'll.
Okay. Very good. So obviously, there is a triangle here. And this is a right triangle. I will denote this by x. I will denote this by y. And let's say we will denote this by w. At any point in time from the moment they start, this triangle is valid. And this will definitely be x squared plus y squared equals w squared, no matter what. 5 minutes later, 10 minutes later, 100 minutes later, 2 hours later, this is a valid triangle. Would you agree? Okay. So this is a function with respect to, very good. This is a function with respect to, right. And this is a function with respect to, right. They all depend on time. So in other words, they're all changing with respect to time. Very good. Okay. So the reason why I asked that is because x is a function of time, y is a different function of time, and w is a different function of time. And it has to be treated that way. Good. So now this is an equation that I could differentiate implicitly. And that will mean 2x dx over dt plus 2y dy over dt equals 2w dw over dt. They are all functions of time. So if I differentiate the left-hand side, I differentiate the right-hand side, and I get 2x dx over dt plus 2y dy over dt equals 2w dw over dt. Let's see what I have. Let's see what I need. And how do I get there? So now let's analyze what we have. What do I have? Do I have dx over dt?
Would it be 20 miles squared?
So hold on. Just do I have dx over dt? How much?
We had the X,
So it'd be
50.
2w dw over
No. So let's talk about if we have dx over dt.
Just be 25.
Why? Say it again.
Just be 25.
Exactly. This is 25 miles an hour, of course. The rate of change of distance with respect to time was given to us from the very beginning. I have the speed of the car going west. There is no discussion that must be, once I denote its distance by x, I know dx over dt must be the speed of the car. Agreed? Awesome. Do I have dy over dt? Of course. This must be 60 because once I denote that distance by y, dy over dt must be the speed of the car going south. Agreed so far? Okay. Then of course I'm going to simplify dividing both sides by 2. And let's see what I'm after. What am I after? You can say, what about x? Yeah, I can determine x 2 hours later. What about y? Oh yeah, I can determine the distance 2 hours later, no problem. Can I determine w? Of course, I'll take the square root from this and have w. So what is the only thing that I need? But that was the question, right? The question was, find the rate of change of this function with respect to time, blah, 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 hours later. Remember one thing, and I'm going to hopefully trigger your memory moving forward. This is at the very, very end of the problem. You cannot make use of it till you have what to plug in? The derivative. If you don't have the derivative, you cannot plug in the number. Okay? So because we are asked to find dw over dt, so this is the question, dw over dt when t is 2 hours. And if you remember, we always said, how can I plug in something that if I don't have that something? So I have to find the derivative first, and then I will plug in. So let's see what we have so far. So we have 2x, I took care of 2, sorry. So I have x. In a minute, we'll write what it is. 1 second. So I have, for now, I have x times 25 plus y times 60 equals w times dw over dt. So dw over dt will be nothing else but 25 times x plus 60 times y divided by w. And eventually, I'm going to determine this, evaluate it when t equals 2 hours. But it's not done yet. Close. So now I have to determine x. And this is determined in reference to t equals 2 hours. And this is determined in reference to 2 hours, and this is determined in reference to 2 hours. So, x. So they start at the same time, and 2 hours later I say stop. Well, I don't, but I calculate their distance. So 2 hours times 25 miles an hour, this must be 50. So x is 50. Then for here, 2 hours at 60 miles per hour, this distance will be.
120.
So now for w, I have to take the square root. I have to take the square root from the distance squared for x squared plus the distance for y squared. So it's this, which is 50 squared, plus this, which is 120 squared. And no, I will not calculate step by step. I will put everything in the graphing calculator and do it in one step. So I have 25 times 50 plus 60 times 120 over the square root of 50 squared plus 120 squared.
It's 130.
It was one.
It's 130 on the bottom.
I think he's saying what
He's saying, yeah. 50.
Oh, okay, that's fine. Oh, that's perfect. Okay, so with the graphing calculator, I put in the square root. I'm sorry, I have the top in parentheses. Parentheses for the top, although you can simplify this fine too. I just want to show you. Please do it in one step, because we introduce more error if we don't. It depends on the numbers, of course, I agree. Close the parenthesis and divide by the square root. And although you may not need parentheses, you know me already, so it's 50 squared. And then plus 120 squared. Close the parenthesis and press enter. So 65, measurement unit. Without measurement unit, this means nothing. 65 what? Miles per hour. So this is the distance. It's a function that represents the distance. So the rate of change, dw over dt, is the measurement unit for the coming from the top over the measurement unit coming from the bottom, which is time. So this is a related rates problem. One more time, what did we do? We created an equation. Without creating the equation that involves the unknown and something else, I will not be able to differentiate, find an expression for W, find an expression for W prime, and then plug in the information I have. You understand that if you put in this and this as 25 times 2 and 60 times 2, when you differentiate, you will get 0. So you have to create an equation or a relationship between variables that are functions, actually, and only then plug in. So always remember what you are given at the very end, find blah, 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 when. That has to be disregarded to the last second of the problem, of the solution. Okay, so any questions on this before we look at another problem? Any questions on this? Is this better, Maddie? Do you understand the question? Can you repeat the question now, or?
Yes, no, I can repeat the question because I get where you're going with it. I thought we were gonna maybe use trig, but I guess.
Yes, we will. We will use trig on other functions. Yes, of course. Let me look for one with trig. Good point.
Bang.
Yes, why not? 29.
Same page.
Yes, 249. Let's read it together. Yeah, there is no end to these problems. I mean, we can, as I said, we can spend. Okay, here's. Let's read it together. Two sides of a triangle are 4 meters and 5 meters in length. And the angle between them is increasing at a rate of 0.06 radians per second. Find the rate at which the area of the triangle is increasing when, and you should close your eyes. After when, you should close your eyes and not look till the very end. When the angle between the sides of fixed length is this. So beyond the word and, when, you should not read till you finish the problem. Because if by mistake you put in that pi/3 anywhere, but at the very last step, you mess up the problem. Okay, so here's the scenario. We have a triangle. We are given two sides of a triangle are 4 and 5 meters, okay, in length, and the angle between them is increasing. Let's call this theta. If we're told that the angle is increasing at a rate of 0.06 radians per second, what does this represent? We did not do this on the first problem because I wanted to give you the idea, but from this point moving forward, we will always have to identify each and every item we are given.
D theta over dt.
Thank you. From the measurement unit, it's very clear that is d theta over dt, the rate of change of the angle with respect to time. Awesome. Let's read on. Find the rate at which the area of the triangle. What am I asked to find before I read on? The rate of change at which the area is changing. So what am I asked to find? Awesome. That's what I'm asked to determine, dA over dt. Okay. The area of the triangle is increasing when, although I shouldn't read past when the angle between the sides of fixed length is pi/3 radians. So this has to be disregarded. I just put it in together so we know what the question is all about. So one more time. We have a triangle. We are given the measures of two sides, and we are told that this angle is increasing at a rate of 0.06 radians per second. Because this angle is increasing, so is the area. of the triangle. Okay, so there are few formulas, actually 3 formulas for the area of the triangle. And one of them is AB sine C divided by 2. What does this mean? You may remember it. We discussed it last semester. I discussed it in my pre-calc class. Exactly. But this requires 2 sides and the angle in between. If we have 2 sides and this angle, I cannot use this formula. So if I have 2 sides and the angle between those 2 given sides, I can use this formula. So this is nothing else but 4 times 5 times sine theta divided by 2. I'll simplify because this is 20 divided by 2. So the area of theta, because actually I should write area of time, but I don't need to. We don't have to write anything because we know both are functions of time. So let me write it maybe on the side for you not to forget. So the area is a function of time. Theta is another function of time. So A equals 10 sine theta. I'm going to erase that A too. So then what do I do?
Right, where do we sine theta over 2 or
20 divided by 2 is 10. I simplified. 4 times 5 is 20 divided by 2, 10. Is that okay? So let's differentiate implicitly. So the left-hand side is, and the right-hand side is 10 times yes, or d theta over dt. That's why we put this on the side. Now and only now I can say when theta is pi over 3, because this is the end. So we have 10 cosine pi over 3. Cosine is the biggest angle of the 3 that I created that little table. And it's not, so it's 1/2, 1/2, square root of 3 over 2, the square root of 3 over 2. So this is the last angle. So cosine pi over 3 is
1?
over 1/2 times 0.06. So this is 5 times 0.06, which is 0.30. Measurement unit. The measurement unit comes from here. Careful. Let's hold on. So what would be the area measured in?
So it's meters.
Radians by second.
The area. What would the area be measured in? Over. That's it. Any questions? Any questions?
So you just put the pi over 3 back in the cosine.
Yes.
theta?
Yes, only
Okay,
here.
1/2.
Because this is given to us, it's fixed. It's 0.06 radians per second. I replace this by 0.06. The 10 is 10. And when I plug in cosine pi over 3, I get 1/2. So what do we say? We say this, that at the very instant when the angle is pi over 3 and the rate of change of the angle is 0.06 radians per second, at that instant, it's the instantaneous rate of change. The area changes, increases, I should say, because the answer is positive, increases at what rate? At that particular instant.
130
Meters per second, meters squared per second, yes. Is that clear? Okay, so let's look at another type now. There are so many different ones. Okay, you want to look at a cone?
Do 7.
Which one?
7.
7? Okay, very good. So number 7 on page 248. Suppose y equals the square root of 2x plus 1, where x and y are functions of t. So I'll write myself a note. X is a function of t. Y is a different function of t. Okay. If dx over dt is 3, part A, dx over dt is 3, find dy over dt when x equals 4. dy over dt when x equals 4. So we have y, the square root of 2x plus 1. Both x and y are functions of a variable t. So now we differentiate the left-hand side, and we differentiate the right-hand side. When we differentiate the left-hand side, we get, very good. When we differentiate the right-hand side, we write, and this, remember, this is one very important derivative, the derivative of the square root of a function. We need to remember this. 1 over 2 the square root of 2x plus 1 times the inside function prime, which is
2
times,
dx dt.
very good. So these two go away. And now I'm ready to write x equals 4. Only now. So it's 1 over 2 times 4 is plus 1. So the square root of 9 times dx over dt, which is given to us. So the rate of change of the function with respect to time when x is 4 is 1. Whatever measurement unit, it's abstract, so we don't have to write anything at this point. Now there is also part B for the problem. Any questions? Any questions? In part B, if dy over dt is given 5, find the x over dt when x is 12. What I recommend to do is go back to the original expression, not plug in anything. So I have dy over dt equals 1 over the square root times dx over dt. That's what I'm going to copy. So dy over dt equals 1 over the square root of 2x plus 1 times dx over dt. What am I going to do now? What am I after? I'm not after dy, I'm after dx over dt. So what should I do to both sides to get dx over dt? Multiply both sides by, that's it. That's all I'm going to do. So I have dx over dt equals the square root of 2x plus 1 dy over dt. And now I'm ready to plug in.
Yeah. What happened?
I multiply both sides by the square root.
Okay.
It disappears from here, it appears up here.
Say it again.
So when I multiply this side by the square root of 2x plus 1, this goes away, and I have to multiply it here by 2x plus 1. So that's how I got to dx over dt equals the square root times dy over dt. Because we wanted to solve for dx over dt this time. So now when x is 12, so let's see what we get. So 2 times 12 is 24 plus 1. The square root is 5. And we are given dy over dt, that is 5. So the answer is 25, whatever measurement unit. Any questions? Let's look at the cone. Any questions on this, everyone? I cannot even begin to explain how many different types of problems we can look at. Okay, 27 on 249. Let's read it together. Gravel is being dumped from a conveyor belt at the rate of, and it forms a pile in the shape of a cone whose base diameter and height are always equal. So base diameter and height are always equal. How fast is the height of the pile increasing when the pile is 10 feet high? Okay. So here's the picture. Here's the cone. So the height, we normally denote it by h. And the diameter, I don't really want to use d because I don't want you to think that it's the derivative or something. So let's give it a different name.
B?
You want to use b for the diameter? That's fine. Perfect. We may not get confused, but it's okay. So gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute. I need to establish what this is. Let's think.
Or D.
That's
Cubic feet per minute.
D of
D what? Exactly. Is that clear? Why?
Yes.
Because of the measurement unit. The measurement unit tells me that when we talk about cubic feet, it must be volume. When we talk about time, it must minutes, it must be time. Are you with me? Okay, good. They say it forms a pile in the shape of a cone whose base diameter and height are always equal. In the process, they are the same. They change, but they stay equal. Okay. Since they stay equal, their rate of change will be equal, right? Okay. How fast is the height of the pile increasing? What are we asked to determine? Because I got to the word when, and I don't want to read it till I write what I need to determine. How fast is the height of the pile increasing? That's it. When the height is 10 feet. Remember, this means nothing now. Where is my starting point? Which function do I have to create? Definitely. Of course. Very good. So let me refresh your memory about the volume of a cone is a third of the volume of the cylinder. The volume of a cylinder is always easy to remember. How do I remember the volume of a cylinder? Here's a cylinder. This is a cylinder. Area of the base times the height. Pi r squared times the height. And the cone is 1/3 of it. So the volume of the cone is 1/3 pi r squared height. Now I have to be careful because I made some changes B is the base, the diameter, so then the radius has to be changed to be over 2. So let's see what we do. So first of all, I know that the height is what I need to keep. Why do I need to keep this? Because I'm asked to find this. I cannot eliminate the height and change it to something else. But I can eliminate the radius and change it into something else.
Change it to B.
Yes, but B is h. So
You
the
make it
radius
squared.
is b over 2, which is h over 2, right? So this piece will become h squared over 4. Do you agree with that? So the radius is b over 2 or h over 2. When I square the radius, which is h over 2, I get h squared over 4. Yes? Agreed? Okay, so then the volume is pi over 3 times 4, which is 12, times h cubed. So pi over 3, the 4 in the denominator, the h squared times h is h cubed. All these problems, I don't think they have a high level of difficulty. They can, but once you read the question or read the problem several times, this should click. Okay, so what do we do next? We differentiate the left-hand side and we differentiate the right-hand side implicitly. That's why we studied implicit differentiation before we got here. Good. The left-hand side is. Do you all agree with dv over dt on the left-hand side? The right-hand side is pi over 12 that no one can change times, good, times, awesome. I'm done. Yes, yes, of course. Of course. But I'm just saying, once I have an expression for the derivative, I can plug it in. Well, I jumped, of course, because I'm after this, not after that. Thank you. I'm not here. I have to solve for the h over dt and then plug it in. I could do this, but I prefer solving first. I don't want to plug it like that. I would like to solve. But yes, you can. You can do it like that. So dh over dt, yes, I will simplify. So I have pi h squared over 4 flip, right? So 4 over pi h squared times dv over dt. And this is where I should plug in h equals 10 feet. So we had pi h squared over 4. So we had to multiply both sides by 4 over pi h squared to eliminate the number in front of, or the quantity in front of the h over dt. So what we get? We get 4. We get pi times 100 times dv over dt, which was given to us as being 30. I will plug this on in the calculator all at once and see how much is the rate. So 4 times 30, of course, it's 120, divide by 100, and further divide by pi. I got 0.0382 approximately. 0.382. Okay, measurement unit means nothing without measurement unit. But this is dh. It's not area, it's not volume.
So it's just
Feet per minute. So at the instant at which the volume of the cone changes at 30 feet, yes, 30 cubic feet per minute, the height of the pile changes at 0.382 feet per minute, as well as the diameter. They have the same rate because they are always the same. Yes?
Could we leave it in radians or would you want it in the decimal?
Oh, you want to, but this is not radians, this is in feet per minute. But you can, but I would recommend approximate it. Yes. This would have been radians if the variable would have been, or the function would have been an angle. But it's not an angle, so it's, any questions on this? Yes, yes. Yes, any questions on this? Okay, let's find another. Oh, yes, let's look at the spotlight. Number 16. Any questions? Any questions? Does it make sense? Okay. So 16. Nico, you still need that?
Yeah, I'm good.
I can give it to you.
No, I'm good.
Okay, 16. So let's read 16 together. The spotlight on the ground shines on a wall 12 meters away. If a man 2 meters tall walks from the spotlight toward the building at a speed of 1.6 meters per second, how fast is the length of his shadow on the building decreasing when he is 4 meters from the building? Okay, so let's start from the beginning. We will read it again and we will come up with a figure. Okay? A spotlight on the ground shines on a wall 12 meters away. Okay, that's what I know from the very first sentence. Period. There is nothing else. If a man 2 meters tall walks from the spotlight towards the building, you know, I can draw a man. He walks from the spotlight towards the building. He is 2 meters tall. And he walks this way at the speed of 1.6 meters per second. We have to establish what this is. And I have to use a notation. He started right here at the spotlight, and he's walking towards the building or the wall. So I would have to denote this by, let's say, x. And I know now what 1.6 meters per second represents. What dx over dt. Okay, I go back and reread it. Let's read it one more time from the beginning. A spotlight on the ground shines on the wall 12 meters away. Fine. If a man 2 meters tall walks from the spotlight towards the building at a speed of 1.6 meters per second, how fast is the length of his shadow? So what am I asked to find? So how fast is the length of his shadow on the building decreasing when, and remember I should have stopped there, the when is always at the very end, when he is 4 meters from the building.
So we're putting that because we don't have a variable for it yet.
Because we haven't established what it is yet. Yes, correct. So now you, yes.
X be 4 meters? Because I mean,
4 meters from the wall.
oh,
Exactly. Perfect. You're way ahead of me. I love it. So then when x equals 8 meters. Fine. So you understand that as this person gets closer and closer to the wall, so here's the person. Okay? You understand now that the shadow on the wall is this. So the closer he gets to the wall, the shadow is smaller on the wall. So obviously this number, whatever it is, must be negative. Negative. Correct. Very good. So I have to create a relationship somehow between what I have and what I want. How do I do that? So I'm hoping that this will trigger your memory. What am I telling you with this drawing? I'm telling you to think of blah, blah, blah triangles.
Blah 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 triangles.
Yes, I'm missing a word.
Right.
Right track.
Nope.
cute.
Nope.
Adjacent.
Thank you. Who said that?
Oh, see, I thought it was like hangman. I thought we had enough letters at the end.
Similar triangles. So in order to show that the triangles are similar, we have to show congruent, we say, or equal pairs of angles. Otherwise, they're not similar. Okay. So I'm looking at the red and the blue triangle. Is this angle common to both?
Yes.
So is this angle the same in both?
Yes.
Therefore, the third one must be the same. Because I was able to show you at least two, the third one has to be the same if I show you two. At least two pairs of congruent angles. This is the same in both, in the red and the blue. And these two are the same because they are 90-degree angles. These two have to be the same. Only now I can say that small triangle is similar. This is the notation for similar to the big triangle. Only now I can write proportions with their sides. Only after I show that they are similar. So let's start because this is very important where we start and how we keep it in order. The opposite of this angle in the small triangle is 2. The opposite of the same angle in the big triangle is? There is no point in discussing these two because I have no knowledge of this and I have no knowledge of this. So the next one you can skip. So now I'm here. Back to the small triangle. What is the opposite side of this angle in the small triangle? Perfect. What is the opposite side of the same angle but in the big triangle? This is a proportion. What variable am I after? I shouldn't say variable, I should say function. But let's say, what variable am I after? Yes, because I want to determine dy over dt. So the proportion that I have is 2 over y equals x over 12. I cross multiply because it's a proportion, and I get xy equals 24. What am I after again?
Why?
Good. Actually, yes. So I will differentiate the left, I will differentiate the right. But remember, we didn't write this. But we know that x is a function of time and y is a function of? Good. So how do I differentiate this?
Differentiate or dx over dt times d
Careful.
y times y
Yes. Plus.
plus x times dy. Oh, no.
Okay. X times.
dy
dy.
Perfect. And
0.
perfect. What am I solving for again? Very good. So then I have x dy over dt equals negative y dx over dt. And I divide both sides by x. Very good. Awesome. So then dy over dt, and in a moment I'll figure out what I need to do. Negative y over x dx over dt. And 15 pages earlier, I had x equals 8. Okay, this is clear. How much? Perfect. This is clear, which is 8. But now I have to find y. No problem. When x is 8, how much is y for the product to be 24? Good. Very good. So then this must be 3. So this is negative as expected. 3 divided by 8 multiplied by 1.6, whatever that is. So 4.8, right? Divided by 8. I didn't need to do anything. So this is negative 0.6. Without measurement unit, it means nothing. Thank you. Meters from dy and seconds from dt. Any questions? I would like to. I'm a baseball fan. I really like it. I would like to work on with you on problem 18 with but we only have like 3 minutes or and a half left, so I'm not going to be able to finish in 3 minutes that one. Yeah, let's do 10. Whatever we can. So 10, a particle is moving along a hyperbola. As it reaches the point 4, 2, the y-coordinate is decreasing at a rate of this. How fast is the x-coordinate of the point changing? So this should take us 2 minutes. I am a baseball fan. So 10 on 248. Last one. So we have xy equals 8. As it reaches the point 4, 2, the y-coordinate is decreasing at a rate of negative 3 centimeters per second, right? The y-coordinate. So what does this mean? How fast is the x-coordinate at that point changing at that instant? So what am I asked to find? Good. When x is 4 and y is 2. Not to be even mentioned. Like we just did. This is really a repeat of 3 seconds ago. The left-hand side is?
dx over dt times y
Plus
x times dy over
which is 0. Good. So we want to find dx over dt. So dx over dt equals negative x over y dy over dt. I move this to the other side and divide by y. Let's see if we have everything. Do we have x? Yes. So when x is 4 and y is 2. We have x, which is 4. Do we have y? And do we have dy over dt? So negative,
Okay, positive 6.
yes. 6. We don't have measurement unit because it's abstract. Oh, I do, I'm sorry. It's right here. If dy is in centimeters per second, then dx has to be in centimeters per second. Any questions?